Okay, so the next lab is a pretty interesting one. Now that we know about the power of the ABI, the application binary interface, let's try to use the same example of counting the sum of numbers from 1 to 9 or 1 to n, and do it in a different way. And let's see how much what do we save over here, and how do we take the advantage of the ABI names of the function calls and things like that. It's a very powerful thing, and let's try to take advantage of it. So we are going to do some small modifications in the C program. If this is our main C program which we had for the summation of numbers from 1 to n, we are going to modify it, and through the C program we are going to pass we are going to make some function calls to the assembly language program. We are going to write an assembly language program in the RISC-V ISA, and then we are going to do some computations over here and send the final results back to the main C program, and we will be able to see exactly the same output that we saw while running an exclusive C program. Okay, so we'll take an advantage of the ABI and see what do we get. This is the concept, and the way it works is the way you interact with the functions. The way the function arguments works is the arguments are passed in two registers, A0 and A1, and it will be returned everything in the A0 register. This particular thing will return you everything in the A0 register. Okay, so let's try to take an example of this architecture, and then we'll look into some more complex ones, but let's try to do a simple one. So the algorithm will look something like this. You have the main program through which you pass the initial number and the final count. So if let's say the C program we are writing the C program, as you know, we are writing the C program to count from to do the summation of numbers from 1 to 9. So we will pass 0 and 10 to the main program. And then the first step is we'll initialize. We can use any registers between A1 to A7. So we will initialize A4 with the 0. So 0 is again the ABI name for 0 register. So we'll initialize A4 with 0. We will initialize A3 with 0. Okay, we'll use a temp register to make all the summation and store and temporarily store all the count over here. We'll store the final count of 10, which came from A1, in a different register. We'll store it in a different register, A2. Then we'll do A4 is equal to A3 plus A4. So in this case, A3 is 0, A4 is 0. So 0 plus 0 is 0. So your A4 will be 0. We'll increment A3 by 1. So A3 becomes 1. And we'll check whether A3 is less than A2. So A3 is 1, A2 is 10. So it's definitely less than A2. We'll go back. A4, which was 0, A3 is now 1. So 0 plus 1 will give you 1. So A4 will be 1. A3 will be incremented by 1. So A3 is now 2. And A3 is less than A2. So A3 is again, this time A3 is 2. A2 is 10. So it is less than, it is indeed less than. Go back and do the addition again. So A3 is 2. A4 was 1. So 2 plus 1, 3. And so on. So it works as long as your A3 is less than A2. The moment A3 becomes 10 by this increment operation, it comes out of the loop, and the final results we want to store back in A0, because that's the function, that's the value that we want to return to the main C program. Okay, so the way we will do it, we know that the final count is there on A4. A4 plus, we'll just do a simple addition, A4 plus 0, and it will store the value in A0. There are multiple ways to do this, to write the same program. We chose one of them. There could be better. We might also come up with a better way to write the assembly language program. Okay, so that's the algorithm. In the next video, we are going to look into the C program, the modified C program, and the assembly language program, which implements this algorithm. This is one of the algorithms of summation from number 1 to n. Okay, thank you.